Yes, I was giving a few minutes extra because I was hoping that Tony Howard, Ian Howard's widow, was going to be able to be here. But I'm not quite sure if she is or not. She may be wandering around campus trying to find us. I'm not quite sure. Anyway, I've given her 5 minutes, so if she comes later, that would be great.
Is the mic on?
Is it on?
No. Oh, yeah.
Is the whole mic on?
Might turn it up a little.
All right. So I have that option. I'm just going to talk like this. Okay, so I'm Lawrence Harris. I'm the director of the Centre for Vision Research, and the centre was founded by Ian Porteous Howard back in the mid or early 60s, so we've been going for a long time. It was called the York Vision Group originally, but now we're known as the Centre for Vision Research, as an organised research unit here within psychology, within York University. Unfortunately, so sadly, he died in 2013, but we're carrying on his memory in various ways. We have the Ian Howard Seminar Room, which is rather too small to have this great big group in at the moment, over in the Sherman Research Centre. And we have this memorial lecture series that we can remember him by in this way. And as I was saying, I was hoping that his widow is going to be here as well. Partly because immediately after this talk we're going to be presenting the Ian P. Howard Family Foundation Scholarship. This is a scholarship for an entry-level student who's coming to CVR, and so we've got that arranged afterwards. We'll just have a little ceremony at that point. Okay, so now to the business of the day. Alan Yuille, very pleased to welcome you here. He received his PhD in mathematics from the University of Cambridge in 1976, where he was working on theoretical physics in the area of quantum gravity under the supervision of Stephen Hawking, who you've probably all heard of. He himself, unfortunately, died earlier this year, in March this year. But he was working on theoretical physics, and Alan was concerned that he wasn't able to actually do any experiments. He wasn't able to actually get data to work with in this way. So he was looking around for a field which was more experimental. And so he went over to the Artificial Intelligence Lab at MIT and in the Division of Applied Sciences at Harvard. So he had those positions there and was working on artificial intelligence from 1982 to 1988. He then stayed on in Harvard as a professor until 1996, when he became more interested in vision, specifically. And as a result of this, he went and became a senior research scientist at the Smith-Kettlewell Eye Research Institute in California. Now, he was there until 2002, and then he went to UCLA in the Department of Statistics, so jumping around in all sorts of different areas here. But he had a joint appointment in computer science, psychiatry, and psychology as well, so very diverse interests going on there. And he edited a book with Randolph Blake known as Active Vision, a book that I think many of us have seen. He moved to Johns Hopkins University in 2016, so just a year and a half ago, 2 years ago, where he is the Bloomberg Distinguished Professor of Cognitive Science and Computer Science. So he very much embraces the aim of the Centre for Vision Research, where we're trying to join together people with all different approaches. And he has all the different approaches in one person. There he directs the research group on compositional cognition, vision and learning, and is affiliated with the Centre for Brain, Minds and Machines and the NSF expedition in computing visual cortex on silicon. So really absolutely connecting vision and computer science. He has an age index of 90 and has been cited over 37,000 times. So quite an impressive CV there. And he's going to talk to us today about deep networks and beyond, vision and machine learning. I'll leave this in case you want to use that.
Yeah, maybe.
Since James wants to be even louder, possibly.
Is that working? Reasonably. Okay, well, it's a great pleasure and honor to be here. I had the luck to meet Ian Howard some time ago, and I remember him as a very warm, friendly person who persuaded me to take part in some really strange experiments. remember visiting his house and seeing all the sort of the toys and things he had there. So it was, very good to be reminded of him. And I'm also particularly happy because, said in the introduction, sometimes I've considered my career a martyr to my interest in interdisciplinary research, and I'm very happy to be here and seeing this really nice, center where you have biological vision, machine vision, and all the things studied together in a coherent manner. And I feel this is a model for how it ought to be done at many other places, including my own. Yeah, my background has been strange. I can't remember how many departments I've been professor in, but what I'm really pleased is I never studied a single course in any department that I've actually been a professor in. Physics and mathematics somehow, those were courses I took place in, but somehow they never given me a job. Psychiatry, wrong themselves. Anyway. Okay, so I talk about deep networks and the art of vision and machine learning. And I have to admit I have a love-hate relationship with deep nets. So the performance is really extremely good for certain visual tasks, and I'll sort of start out by describing some of the tasks that their performance is very, is fairly good on. I would say their lack of interpretability is worrying, need to understand them, diagnose them. I'd say perhaps on the positive side, they are a rich and constantly evolving class of techniques. Just when you think the final thing has been said on deep nets and they morph into something else, and there's a very, rich, evolution of what they can and potentially do. And I would say they're very useful, but not sufficient to solve vision, and so I'll emphasize that more as we go along in the talk. I would say, given the interest of the audience here, I'm going to talk mainly about the sort of what I consider the AI side of developing models. I'd like to develop models of vision which have the same capabilities as humans, and there is some sort of psychophysical studies, but they're not really ready to be presented yet. There's also some work with some of this, some collaboration with Ed Connor in Neuroscience at JSU, but again, that's interesting, not ready to discuss it yet, so it's mainly going to be on the computer vision or the sort of computation modeling side. By the way, I also welcome any questions during the talk. It sort of makes it easier for me to interact with people and know if I'm talking at the right level or going too slowly or too fast or something like that. So what can deep networks do? So here is one picture of a deep network, takes the input image and then sort of gets a hierarchical set of features. This is BTGNet, and finally it gives in this case, a classification into I don't know how many objects. I think this is ImageNet, so it's like 1,000 objects. This is for classification. You have them for detection and classification. You have them for semantic pixel labeling. You have them for almost anything by variants of the same idea. And really, the critical thing about them is first they're hierarchical, so they can extract information from images at different levels. And they do it by using features which, rather than being sort of hand-coded or hand-designed as features were in the past, are learned, which can be good, or the argument at the best it's good because they adapt to the complexity of the world rather than being the choices that some human design was made. But on the other hand, that's, learning is a two-edged sword. It can be bad because they're overfitting the data, and I'll get onto that a bit later. But the critical thing that makes them so useful is that the output is a differentiable function of the input and the weights. So if you just change the weights a bit, you can change the output, you can differentiate the output, you can you can propagate the errors, and you can modify and learn them. So basic idea of how you can learn them is incredibly simple, even though the practical details of it are not. But if output's a differentiable function of the input, it just tells you which way to go down here or to improve the results of the weights. Examples of cases where it works well: face recognition, text recognition, medical image analysis. Face recognition systems will work on billions of people these days, which is pretty impressive. One of my ex-students has a big company and is one of the top ones in the world with that in China, and it's quite impressive, really impressive to see what can be done there. It doesn't mean necessarily that you can solve face recognition under very complicated lighting situations or with people who are really trying to hide their faces, but with reasonably cooperative subjects, the scaling is incredible. Medical image analysis, I'll just mention a little bit about that, because this is an example of a very, from my perspective, sort of applied problem in medical imaging. And here you have image scans, you have data, you have annotations, you have people telling you what the ground truth is, and on the other hand, then you train algorithms which take this data and you try and predict the ground truth. In this case, well, I think there's a nicer slide here where you're trying to find the pancreas and other organs which frankly, I never really knew existed until I got involved in this project. The team is, and I say for real applications of machine learning, I think it's important to have experts in here. So we have a whole bunch of radiologists, Dr. Elliot Fishman, who's a real, really one of the top radiologists around, oncology, pathology. We meet every week on this. And here's the data connection. Here are all these strange organs for liver, pancreas, kidney, blood vessels. You get these annotated spleen, gallbladder. You get them annotated in ways like this, and then you throw deep networks at it and see how well you can find them. Sorry. About that. And the results of these are just very effective. I mean, it's working within the data set that you've got. The data set was several thousand images from Johns Hopkins. And the question with all machine learning is how representative the data set is of the set of possible things that can happen, and no one really knows that yet. But this is an example. I think the amount of variability of the data is not as big as it is in natural images, and it's at the stage where it's at least believable that deep learning methods will not only work, but will work at human level, except, not as good as a real expert as Elliot, but as good as, an almost Elliot, and will maybe make Elliot's life simpler by using it as an assistive device. And so here you're getting prediction recordings, performances of, 100%. This would be for detecting and segmenting these things. 100% would be perfect. You don't want 100% because the ground truth is not perfect anyway. And so you're getting up fairly high. The variabilities on some of them are due to the fact that, in fact, certain of the boundaries are really unclear. So it's a bit like labeling the boundary of your hair. There's a certain level of imprecision on there that's inevitable. Finding the organs is only the first stage, though. Is what you want to really do is you want to start finding the tumors. Here's an example of a tumor. This is ground truth in red. There's the estimation we have over there on the right of the tumor and of the healthy pancreas. And so we're treating, detection of these things or early diagnosis of cancer as a sort of segmentation process where you first construct a representation of the input-output, and then you have a fairly simple decision rule to say, does this person have cancer or not? And this advantage of this is it is to some extent interpretable. You say the person, you think the person has cancer because you think there's a tumor in that area, and a radiologist could look at that area and see whether that's correct or not. And it's sort of not completely interpretable by any means, but you're proposing bits of it which people could come and check out on. Strategy, quality of segmentation decreases if you look for the tumors and dilated ducts, etc. Die score 60-70%, sort of 70% overlap. That's not perfect, but these things are small, these things are difficult. Classification performance has extremely high sensitivity and specificity, sort of 99 or 96 times 7, 98, 99. False positives seem to be explainable. And so if you see where the deep network makes mistakes, you show it to Elliot and Karen Horton, who's another expert radiologist, and they will say, occasionally they'll say we can't understand that at all, which is worrying, but almost all the time they say no, that's some sort of structure that looks somewhat tumor-like. Focal fat seems the catch-all term for that. And then other issues of false negatives. So I just bring that up as one example of something that's, of which, you know, and it also a sort of a work example of throwing a deep network at something. The requirement is, as a project started, I said, okay, we can do this, provided you give us nice annotated data. How much? I didn't know. I had to make a guess. You know, we said about 1,000, and the issue is 1,000 big enough to be representative? We don't know. We'll start with 1,000 and then work and scale up after that if we don't know. Okay, so that was one example. Then I thought what I'm going to do is I'm going to go over several topics, each of which would be a full paper, I think one of which I'll probably skip for reasons of time, but they are maybe interesting or provocative or make people think, and some of them relate to topics that were brought up during my trip here. So why are deep networks deep? So this is work by Sue-Ann or Joe, and you know, it's an obvious question, deep networks, why are they deep? Well, because Jeff Hinton likes making jokes, and deep networks are obviously better than shallow networks, so there's that reason, but really, you know, scientifically, a deep network is good. You know, deep networks consist of linear operations plus non-linear operations of, you know, ReLU or thresholds, and the old ones used to consist of linear and then sigmoid functions. And like stacking a lot of linear things on top of each other doesn't really do you much good, because all you get is a linear operation. So what you want to do is arguably to increase the number of non-linearities in there, because that's what actually does the work for you, as well as the fact of increasing the receptive field size. A neuron at a low level of the network only sees a small amount of the image. A neuron higher up sees a larger amount of the image, and in a way that design typically has more non-linearities in it. Okay, so this would increase performance. Right. Here is the standard deep network design. I showed that earlier. And there's a standard design where you have a series of channels, around 200, 512 of them, and so you can see these little rectangular blocks. This axis is sort of X position, Y position, and the depth is the number of filters. So you'd have a whole set of filter banks, which of course when I started were usually Gabors and things like that. And in fact, in many deep networks, the things you learn at the lowest level are indeed Gabors. So they have, you know, that type of structure. However, the issue in the standard deep nets is that the layers are all updated simultaneously based on the input from channels in the previous layer. Now this may seem sort of a natural thing to do or obvious, but it has several effects which are slightly undesirable. One which is not so obvious, well, it doesn't seem to matter much, is that every neuron in each channel at each layer has the same number of non-linearities as any other neuron in a different channel at the same level. Okay. So, so that's the standard design. But, and the problem with that, which is jumping ahead in another slide, is that it means that the deep network has an enormous amount of symmetries inside it. You know, you could just reorder the channels. Channel 1 becomes channel 2, and channel 3 becomes channel 7. You just commute them. And those would be actually equivalent deep networks in terms of the input-output function. So there's any deep network can represent the same input-output function in an incredibly large number of different ways, which are all equivalent. And so if you think about this, this is possibly wasteful, because you know, you only want to represent it once. But also it causes problems when you're learning, because when you're learning your training, you have stochastic gradient descent, which is a very nice algorithm. But it does mean that for every minimum of the, you know, every solution, there's a whole enormous number of other solutions, okay, that are equally good. Now, at first sight, that shouldn't worry you, because then you say, hey, if I get into one, it doesn't matter which one I get into. But if you think about having an energy function like this, with a minimum here and a minimum here, then in between there's got to be something joining them, which has got to be a saddle point or a plateau or something. And so that means that you've got an energy landscape which is potentially very complicated and messy. You know, getting into, as I say, it's nice, it doesn't matter which deep net, which minimum you're in necessarily, but you may get stuck and you're learning in a saddle point or somewhere that's caused by having so many local minima. So that's a problem, potentially, and it could be one reason why, in practice, some deep networks are difficult to learn. That the energy landscape is so complex. And so, can you then get large depth without needing many layers, is a question, and then can that actually affect this sort of the symmetry problem as well? So, my student Joe, who was interning, and people were not taking advantage of him because he was very clever and they were getting to do some rather boring stuff, spent his spare time during his internship sort of thinking about this. And so questioning the standard design, channel 1, channel 2, channel 3, here in green, outputs, channel 1, channel 2, channel 3 in a standard network. Here you could just permute the channel 1, channel 2, channel 3 will be equally good solution. This is a symmetry, this is a problem you don't necessarily want to have. So the suggestion is, okay, why does channel 1 in blue get input from channel 1, channel 2, channel 3? It's going to have a certain receptive field size, an additional non-linearity, but then channel 2 in blue gets input from the blue channel 1 and the green channel 2, channel 3, and so it's got more non-linearities, it's got a bigger receptive field size, and you can't really replace channel 1 by channel 2, they're different. Channel 2's got 2 non-linearities, channel 1's got only 1, and then you do it with channel 3, that's got 3 non-linearities. So what it means is you're going from one level of channels to the next level of channels, you can get you can squeeze in more non-linearities and bigger ranges of receptive field between one set of filter banks, and the channels and the other. And at the same time, you sort of reduce the amount of symmetries in the whole system, which may make it easier to learn because you've got presumably a nicer energy function to minimize. So the hidden symmetries, this is where I jumped ahead. Maybe deep nets are badly designed. Quite like having provocative titles like that. What I've done is sort of a hand-wavy description of symmetries maybe being particularly bad. There is a way of trying to quantify this a little by a concept called overlap singularities, which people have studied a bit. And basically, if 2 neurons start doing the same thing and feed into a neuron power up, that's an overlap similarity, they're doing the same thing, and the learning becomes more difficult at that stage. Okay. And so here you can sort of prove with this particular method that form of overlap similarity does not happen, and so and so at least that's one problem of learning that's been identified for standard deep nets, and that's reduced here. Does it lead to faster learning? Well, we can show curves suggesting it does. GUM is what we've called it. It's in red down there, the standard ones in blue up there. This is sort of some sort of evidence for it. Not completely convincing, but it's sort of on the right path from that. Does this perform well? Well, it does perform as well as other bigger, deeper networks which are not, which are more based on the standard design. Okay. So this was, that was a CVR paper, and I guess the issue here is, well, maybe there are better ways to design deep networks. Maybe getting rid of the symmetry property is nice. I had a fantasy for 5 minutes to say, well, could you make a deep network convex so it's guaranteed to converge? Until Joe told me, no, there's, Alan, don't be crazy. That's far too good to be true. Yeah.
Yeah, one question. Is this an end-to-end network?
Yeah. It's an end-to-end network. The training is a little bit more complex than the training of other ones because, the other ones are, updating all things at the same time. but it's an end-to-end network. The other advantage of it, it needs less memory than the existing systems. After you've trained it, the updates from one set of channels to the next set of channels, it's about the same number of parameters you had in the previous type of architecture, but as I say, they've got far more nonlinearities, they've got bigger receptive fields, and they can, and far less symmetries. Anyway, the next one I think I'll skip. This is combining deep networks and random forests, unless anyone's really majorly interested in this. It's just in my community, just very briefly, random forests are a very good algorithm for doing things. Deep networks are a very good algorithm for doing things. It's, can you put them together? The answer is there was a paper by Constantine, we're told, that did it for a particular case, and you can generalize this. So you can train a deep network with a random forest at the same time, and it's got all potential advantages. But unless anyone wants to know more about this, I'll skip it over for reasons of time, because there are certain advantages of it that are a bit sort of technical. Okay, then moving on to Pew Shot Learning. So, a problem with deep networks is that they require supervision, and supervision can be difficult to computer vision because you have to annotate things, and certain things are very easy to annotate. It's very easy to draw a box around a cat. It's harder to label which pixels are a cat. It's harder to label the depth or the 3D shape of the cat. Very, very difficult. And also it's frankly inconceivable that humans or primates could learn using full supervision like this. So the next two parts will be sort of ways of trying to reduce that. And so the first one is Pew Shot Learning, and this actually again was spearheaded by Joe, and the case there is you have too little data available for training. But it's a little bit more complex than that. It's supposing you had quite a lot of data for certain classes which you call multi-class, so many, in this case, many objects that you know of and you've learned how to deal with them, and then somebody gives you a few more objects that you've only got a few labeled examples of. And so the idea is you want to exploit the fact that you've already learned the deep network for a sufficiently large number of objects, and then when something new comes in, you can exploit that and need fewer examples. So you can try and relate this, at a very hand-wavy level to how infants could learn. Infants take time to learn things, very slow period, and then suddenly they accelerate enormously. And so at a very, intuitive level, maybe they're sort of building up dictionaries of patterns, and where sometimes when the dictionaries become sufficiently complex, sufficiently rich and representative, then they can learn new things from those dictionaries. And the same, idea would happen here. The deep network can learn certain features, hierarchical features that correspond to parts of the objects, and then you have a new object in that's built on similar features. Even though it's a different object, you can describe it in terms of the features that you've already got, and then you need a very simple, you only need a few examples of it to learn. Okay, so roughly here, you can just say with the deep network, there's a whole series of layers going up, and the final layer, in this case, would be the classification. Is it a dog or a poodle or, whatever? And so the activations here would be the penultimate layer before you make the decision. And so you have learned these for the examples that you've got already, that you've got many pieces of data for, the pug, the jay, the hen, etc. And you've learned all the way to the activation. And now you're shown a few examples of snails or corgis or other things, and you want to learn the network things in green. So the first thing you can do is you can assume that all the weights up to the final layer are the same for these new objects, which is roughly assuming that the new objects are, they can be described represented by similar features. So this wouldn't work, for example, if you trained it on vehicles and man-made objects, and then showed as an animal or two, it would then be rather unlikely that the features for the that you want for the animal would be the same as the ones you want for that you've already got for the vehicles. But you know, assuming that you've tossed in enough examples of different types, this is perhaps a reasonable assumption. So you can think that the activation levels here are probably quite good, but you know, then how do you combine them to get to the next stage of of classifying the things as snails or corgis? So there are certain ways of doing this. You can go back to very old-fashioned methods like sort of nearest neighbor clustering. You can say that the features that you get for one object are likely to be the same for other examples of the object. They'd be in the same part of feature space, so you could do nearest neighbor, and that actually works. You know, it's not terrible. But the idea here was that what you could do instead is that you could actually use the patterns of activations here to predict the weights up to the next layer. And this should sound a little bit strange at the first sight. You've got the activations of the penultimate layer, and then you actually want to predict from those the next set of weights which give you the decision. Okay. It's not so crazy if you think of the nearest neighbor idea, because the nearest neighbor idea, you could do that anyway, but it is sort of a little bit strange, perhaps at first sight. But then if you look into the weights, into the activations, you see in fact that I forget which one is the activations, which one is the weights here, but the point is it doesn't really matter. They are actually very similar, the same patterns are there. Over there, the objects, the one that's yellow, I've forgotten what object that is, the green, the purple, they're roughly in the same part of the space, and that's roughly saying that there is sort of a relationship between the weights, the activations that they typically have, and the weights that make the decisions from them. Okay. So this is sort of partially empirical, so it can be interpreted a little bit as trying to understand what's happening in the deep network to some limited extent. But in this case, what you can do is saying, okay, there's a relationship between them. For the examples where you've seen many examples, you know, for the cases where you've seen many examples, take the one you've seen many examples of, activations, predict the weights for those, and use that same function to predict the weights for the classes that you only have a few examples of. Okay, and so that actually works really well. There's an empirical relationship between the activations of the deep network features and the weights of the decision layer. These can be learned from the examples that you've, the objects which you've got a lot of, and they can be applied to the new examples, new objects where you've only got a few examples. So there's sort of two things going on here. One is if you've learned on enough objects, you've got a rich enough representation that could probably work as a representation on new objects. The second, somehow from that representation, you could actually predict the decision weights directly. And that will work well on these objects. So here, what we're doing is just sort of systematically reducing the amount of learning involved, the amount of teaching involved. The amount of learning remains the same, but the amount of supervision. And so one bit I wanted to put in here, which is very recent work, and this was actually mainly a summer project done by my student Chen Xu on the left, but at Baidu Research, where one of the people developing it, pushing it, was somebody called Peng Wang, who had been a student of me at UCLA a few years back. So he's sort of an ex-lab member, and so the motivation for trying to do unsupervised deep networks, from the artificial intelligence side, is annotation is very hard for some visual tasks. To get it for optical flow, you need to do detailed correspondence. That's not easy to do. For depth estimation from a static image, that's not easy. You can use LiDAR or something to estimate depth, but it's a rather painful process. So hard to do for computer vision. And then for interest in biological vision, it's very hard to see how you could actually get that level of supervision that traditional deep networks learn, just inconceivable really. It can be done that. However, there's been some work in the last few years which trains deep networks, and optical flow I'm putting down because that was the first example I saw it of, where you don't actually have the supervision. You do not have the pixel, the velocity label, motion optical flow label at any particular position. Instead, what you have is sort of local statistics of what it's like. So the history of optical flow algorithms, going at least from the computer vision perspective, but I think also the biological vision perspective, is you have local cues for the motion, for the optical flow, and then you have sort of slightly more non-local cues for putting them together, which are typically smoothness of the optical flow, sometimes smoothness plus slowness, and there's a whole bunch of studies about that. So here what you do, what people showed, is you actually could learn something to estimate optical flow by just giving it a whole set of video inputs, and by imposing the constraint that at the top level the optical flow is fairly similar at neighboring places. So I was a bit surprised when I first saw that, but it's correct. It doesn't work as well as something that's fully supervised, but it works generally quite well. So other people then extended this, and I think at the last CVPR there were several papers where you can assume that you can train a deep network to estimate rigid depth from ego motion. So you imagine a camera or a person moving around in the world, ego motion, the scene is going to change, most of it rigidly due to your motion relative to it. And again, you can have a model that doesn't know the depth or something like that, but knows this sort of relationship that people had had figured out in the 80s. And by doing that, you can train a network so it's actually assuming that sort of model of the environment, but then estimating the depth directly. And so I guess for me, in short, realizing this means using 1980s computer vision to train deep networks, but without having supervision. So the earlier work was done by optical flow, was done by various people, and this thing about depth from ego motion, Pen Wang's name is on several of the papers for doing that. So I like this because I like idea of training deep networks without supervision, and I also like the 1980s computer vision models because I think they were quite insightful and useful, and it's nice to see them, they've got a role here. So the recent work then, this project, which is not, is submitted but not yet published, was sort of building on this work to use unsupervised deep networks to learn and combine several different cues. So one cue is you could do unsupervised learning to learn optical flow. Another one is you could use it to do structure from rigid motion. And the third one is you could try and do this sort of classic vision problem of shape from X. Shape from X is what shape you get from a single image. And you could train these all in a way that was together. You could fuse them together in a way that made things consistent between them. Because the optical flow, most of it or some of it is due to the environment changing, so it's got to be consistent with the rigid 3D depth you're estimating. Some of it is not, because though the environment is mainly static, there can be some dynamic things moving in them, and so you'd like to start picking those out, and those are the ones that whose optical flow is not going to be consistent with the rigid motion, and that sort of comes out from this as well in some way. Then there's also the shape from X, and so for people, my generation, or people who did vision in the 1980s, there were all these things on shape from shading, shape from texture, shape from perspective, and the sort of the dirty secret of them is that they only worked on rather restricted sets of images. People were doing shape from shading. When I came to MIT, they would take objects, they would paint them with matte paint so they have nice Lambert reflectances. They put them somewhere, you put a light source away from that, and then shape from shading would work. I mean, it can work in more general situations, so there's been impressive work where you can get it to work on faces, which are roughly Lambert, etc. But most patterns of shading that you see in the real world are not due to the Lambertian assumptions that you had in those models. You know, they're due to light sources being at, you know, finite distance and stuff like that. And so the shape from shading classic would only work in very restricted situations. The same would apply for shape from texture. The same would also apply for shape from perspective, although that would relate to what sort of environments you're in, and there's certain things like Manhattan worlds, and I was seeing Jay Melville's recent work on that. It will work fairly well under those situations, but still, none of those cues worked in general. And also, even worse, many of them didn't output whether they were really working or not. Okay. So this is at the level where the deep networks were particularly, perhaps potentially impressive, because you could train a deep network on the input and the output. There were problems with that because you needed to have the input and the output, and you didn't often have the output. There's problems with interpretability, but I was persuaded, partially because Pen Wang, when he was working with me at UCLA, did work on this, and the argument about why the deep networks could do it was basically memorizing. You can memorize certain patterns that happen in the images, and you could store the fact that this pattern corresponds to something with a particular orientation in the world. You know, that's a conjecture for why it might work. It's not completely proven, but it's sort of like a working hypothesis. So I'd argue that for shape from single images, it's possible that deep networks might work well because the other methods do work under certain restricted assumptions, but they don't work in general. Although how to combine them in cases where they do work well is an open question. The value here then is, okay, so if you do that, how do you estimate depth without supervision? And you can partially do it by using the same assumption that local depth is probably locally similar. You know, this is a standard sort of weak constraint of smoothness that came up in a lot of vision algorithms, particularly in the 1980s. So you can do that. The secondly, in here, once these systems start working, the rigid structure from motion can sort of give you the estimate of the depth of the shape for certain classes of objects, and then that can be used to supervise the depth from single images. This is provided combined with the idea that the deep networks can do this by a type of memorization process. So, nevertheless, whether that's right or wrong, you can build systems, and to evaluate them, you do have to have something with ground truth, which means you do it out here on this so-called kitty data set where people have gathered ground truth, because people like automated cars. Companies will put in enormous amounts of money to do these things, so they will create ground truth data sets, and they may sometimes they'll share them with the universities, and you are getting out estimations of depth, optical flow, and the positions of the bounding objects. So, and there are evaluations on this, and I'm not going to bother you with the evaluations. Here you've got things estimating motion, which, you know, assuming rigidity, you're estimating the orientation of the camera, etc. Something estimating the flow, something estimating the depth, and the HMP, which is sort of really trying to make sure that the depth you estimate is consistent with the motion, and also that it will partly predict the image intensity of the next frame. So, so the work is good, and I think what it does is it uses simple computer vision models to train deep networks. And sometimes realizing this, I started kicking myself because I had a paper with this guy, Stenis Manakis, in 1994, which I think is cited once, and that's almost certainly by ourselves. We'd sort of had a slightly similar idea before data sets came along, and we never did any follow-up on it. But you would take a classic, you know, model like estimating the velocity flow and smoothness, you'd say the output, the estimate should be a nonlinear filter of the input, and you could train a network to do that nonlinear filter, provided you had training examples. In those days, we didn't have big data, so we didn't have training examples, but the model we were doing was a Bayesian model, so that meant we could simulate it and generate training examples, and then we could train on it. So I started realizing, damn, that paper should have done more on that paper at that time. But anyway, it isn't, it's sort of, I think there's a very nice connection there between certainly using the classic models for training without much supervision, and also in this case of how you could start combining them holistically. And then it does suggest, a sort of, and this is again sort of hand-waving and speculative, a strategy that the visual system interacting with the 3D world might be able to sort of bootstrap itself up. Now this thing is called unsupervised learning, and I even put a question mark originally after unsupervised every time, except I thought it looked a bit ridiculous, because it's not using no assumption at all. It is using certain assumptions like local smoothness and sort of factorizability. And so, it's not, you're not getting something for nothing, but you're getting perhaps a lot from very little. And you could just about conceive of a situation where a visual system would sort of explore the patterns of intensity that you have with simple rules, and might find smoothness is a likely thing to happen, and factorizability might happen, and it could bootstrap yourself up. And I think David Mumford had a speculation in a chapter in a book, Neil Richard's book, about that, more based on stereo vision. You have an image in your left eye, you have an image in your right eye, and then you start realizing that two images, if you superimpose them, you just have to warp one slightly and it becomes like the other one. And so you discover disparity by the warp, and from that you discover depth, etc. This was, from David, this is a very speculative thing, but it's sort of, you start wondering about that. Could you bootstrap your way up by learning using motion cues? And I think the literature on on learning is that humans, infants like motion cues first before they like anything else, and maybe you can do a sort of rather a form of learning over time like this, which then you can get out objects, and you can maybe start tracking objects, you can learn objects from that. But we'll see. This is maybe me just getting excited because of this recent work. Now I'll move on to attacking deep networks, and maybe I need to see a little bit how I'm doing for time. But we started a bit late. 5 or 10 more minutes. Yeah. Okay. So attacking deep networks, I think, is a way to understand them and strengthening them, and I distinguish between local attacks and structured attacks. Local attacks are very small changes to images which cause deep networks to make very big mistakes, or structured attacks are everything else. Here's a local attack from my group. You add a little bit of noise onto these dogs, and they turn into cows, and their shape changes. And even more dramatically over here, these two trains turn into airplane, and their shape is the logo of the conference which we submitted this paper to. And this blank screen, you add a little bit of noise on, and it turns into the shape, it's a bus or something, and its shape is the shape of the year of the conference. So you can do these sorts of tricks, and you can do them precisely because the deep networks are differentiable functions of the input, and so you can use that to learn adversaries. But you can attack them, you can defend them by doing things like padding, and there's a rather nice, this is Xiang et al. Had a defense second prize last year, and then this year, just a week ago, there was a stronger defense based on partially on some work from MIT and others, and you seem to be able to defend not perfectly against these sorts of attacks, but if anything, it makes the deep network stronger and does better. So I think those types of local attacks are okay, but I think they're only the tip of the iceberg, and I don't worry about them nearly as much as I worry about other ones. So here is a picture, and I know this relates to some work I've seen visiting here, but here is a monkey. You get a motorbike, it turns into a human, a bicycle, it turns into a human, a guitar, it turns into a human, and also the guitar turns into a bird. So what's happening, it seems the deep network is somehow exploiting context in a way that it shouldn't, in a way that may make sense in the data set, but not in the situation, not in a situation where a human would have no difficulty. We then motivated us to try and develop a sort of a challenge that you wanted to detect the semantic parts on an object, and you are only able to train them on cases where the object was fully visible, but then you wanted to test when the object was occluded. Because I think occlusion, I've seen a paper from here saying, you know, occlusion is a dirty secret, I can't remember, elephant in the room. Yeah, I think occlusion is a way that you can destroy many deep networks, and I think it's something that happens an incredible amount, less so in computer data sets than it should. And so we did various work here using a method called visual concepts, a thing called deep voting, which was sort of like an adaptive algorithm in the sense that it could automatically decide whether to ignore context or not. If it was helpful, it could keep it in. If not, it could reject it. And if something was included, it could decide to switch it off automatically. Not the final solution to these by any means, but it was a method of varying the network to make it more able to deal with these things. Only works with semantic parts, and it would outperform things like deep networks. This is where we have sort of some psychophysics stuff. You get examples of images where deep networks can't recognize them at all, but humans can, and then try to see if these models could actually recognize them. And explanations and follow-up work, so maybe I'll skip over that. So attacks at the very local level, and then sort of attacks which are more non-local, by putting in occlusion or doing other things. So that moves me into, perhaps, for me, one of the more interesting things is the issue about when is big data not enough? Are the fundamental limits of the current methods, meaning things like deep networks, or even the way that the computer vision community evaluates these things? So limits to functions a deep network can do, weaknesses to certain adversaries, and I'll concentrate on limits to annotated data sets and big data. So my claim would be, and you know, some deep network people would hate me for saying this, that deep networks are ultimately sort of fairly memorization devices. Not perfectly, but they're memorizing certain types of patterns. They can interpolate between them. They can't really extrapolate outside them. You know, humans can recognize a blue tree even if you've never seen a blue tree before. Deep networks can't do them. So there is a limit to what they're doing. It's hard to pin down mathematically, but from experience working with students, you know there are some things deep networks can do, and sometimes you ask them to do too much and you can't learn it. Okay. And of course, they don't have any causal understanding, and an analogy here is between Ptolemy's model of the solar system, where you have epicycles that will predict things wonderfully well, and Newton's laws, where you can understand deeper causal understanding, where you can see where the epicycles came from. Ptolemy's system would not work on a solar system elsewhere. Newton's laws would, we assume, of course. Being a physicist, I'm occasionally skeptical. Maybe our laws are any later also, but in general, Newton's laws would also work for our solar system if some mammoth alien spaceship came in with enough gravitational mass to disrupt our solar system. So the underlying laws of Newton would be more understandable, more predictable, more causal. For vision, what's the analogy? The analogy would perhaps be parts of computer graphics. You can render images using three-dimensional shape models, lighting models, appearance models. Images are ultimately caused by things out there in the real world, modeled in that way, generating the images, and the computer graphics community has developed methods for generating almost any sort of image at the moment. So those are perhaps the underlying causes. Limits to the annotated data sets, the state of the, how computer vision papers are accepted is basically how well you do on annotated data sets. I think that's highly problematic because it biases the system to vision problems for which there are data sets that are high profile. Even trying to put in a new data set can be problematic because the reviewers would say, nobody's ever used this before, so, and what can you say to that? Except that if we said that in the 1980s or 70s when computer vision was started, we never got started at all. But anyway, so image data sets are, bias the community by what's easy to represent and what's easy to annotate. Also, they're only partly representative of the complexity of the natural images, and this gets back to a really critical point. Are the data sets we're doing for these CT images big enough to give us systems that can find tumors in almost anyone when they come into a hospital or not, we don't know. I'd say it's possible that the ones we have may not be enough, but maybe a little bit extra may be enough. Are they big enough to do face recognition? I think the answer is yes for cooperative subjects, but for other tasks, are they? Very unlikely. Rare events may be unrepresented. Automated cars, you train the system. Do you have images where there's a baby lying on the road? Not very often, or not at all, and so your system will not learn to deal with that. Experimental design, can you vary the lighting factors, viewpoint, the lighting, the material properties systematically in the data set? No, you can't. Not in a real-world data set. But you'd like to do that. So I claim that for some visual tasks, the data sets may never be enough to cover deep nets or for any standard machine learning sample. I think the size of the data sets to be representative of the complexity of the visual world would get combinatorially exponentially big. And then there's no way anyone can have a data set that big. Facebook, Google, Chinese government, startup companies, it's just not possible. You can't store that amount of data, and even if you could store it, you can't train on all of it, you can't test on all of it, you're really stuck. And I think the basic assumptions machine learning will break down, which is that you have a data set, it's representative, you train on part, you test on the other part, and that's just not going to happen. You can't do it. So here's a toy example for using computer graphics. You synthesize it. Here was the idea of images you could have in your data set, images you couldn't. I like the student who made this, but I said this is really misleading. It makes the point, but I mean, icebergs, 90% is underwater. I say the set of images you can have that are not in your data set, this is 99.99999, whatever. It doesn't stop here, it just keeps on going right down to the bottom. So the ones you've got are only a small fraction, a tiny infinitesimal fraction of the ones you're going to need. Now, depending on what task you're doing, the fraction may be enough, and this is the issue about medical images possibly, or face recognition, but for other things, I don't think it's going to be enough anyway. So just take a simple computer graphics model, 4 camera positions, lighting, texture, material, scene layout, I think 11 parameters, 10 to the 3 possible values of each, and you get 10 to the 39. Now, I guess people, you can't really store that, and that's for a single object in one environment. Now, maybe you don't need all these images, maybe some of them are so similar to each other that you need to sort of just check a limited number, and maybe 10 to the 3 is enough to sort of solve all these densely. That's unclear, but this is only a single object with a single back, with a set of 3 different layouts. And so objects, a single object, I'd argue could be occluded in an exponential number of ways. You pick a certain number of possible occluders, anything you can think of, and you can put them in any number of positions, and you've got an exponential number right there. The deep vote method I mentioned earlier was a way of attempting to deal with that, as having something that was robust and could switch it off. But still, you don't know if that's there's only a partial solution to it. And then the image itself can be constructed in combinatorial number of ways, taking objects, moving them around, and you're getting exponential complexity there as well. Text captioning is an example that we worked on. So, I do find within the computer vision community, the fact that we can get deep networks to work makes it easier for me to criticize them. Otherwise, I say, okay, Alan, you're over the hill, you don't know how to do these things, you're hung up in the 1980s, but since we can still get these things to work, the people will take the criticisms a bit more seriously. So text captioning, you have an image, and you want to output a text, you can do this, it's nice, it got written up in the New York Times, but does it really work? The answer is not really. It will capture it for some of the examples, but for others it will have mistakes which are really catastrophic. And why? I would say that as soon as you try and, here maybe it's okay, you've got an orange in a cup, bowl and nothing else, but as soon as you start making it any size at all, there's an exponential number of possible configurations you have, unless there's something marvelous about the world that reduces that to a smaller number. I just don't see how you can do it with these current methods. You know, you can keep on improving the thing, turning the handle. I had another student who started out by doing this, and I think persuaded him, no, this is not a good direction to go for. Experimental design, I was embracing computer graphics, as came up before. Can deep networks trained on ImageNet really detect surfers? Well, you take a computer graphic thing, you take your sofa, you turn it upside down, you rotate it, and you find that you can break the system. You know, you can get configurations which the deep network trained on ImageNet cannot do because it's not seen them. You know, and how can you show all the possible examples of an object under different lighting, etc., and also, you know, and then with occlusion as well. Stress testing algorithms, stereo algorithms work reasonably well, but you know where they're going to break down. They're going to break down if you're driving a car in the rain because there's going to be specularity that's going to mess it up, or there's going to be trucks and they're going to have large areas of no texture. Can you test algorithms like that on standard data sets? No, because people don't label those things and they don't happen often enough to really matter. But you can do this in computer graphics. So we developed systems where you could stress test algorithms by systematically varying these things, followed by experimental control, and then you could see which algorithms were robust to them or not. So I think, you know, I think we move into a stage where big data and deep networks are not enough, and we need algorithms that can generalize, extrapolate away from the training examples, which for me means things like compositional models of parts you can stick together, models that factorize geometry and appearance, shape and appearance, geometry which is fallen a bit out of fashion in computer vision. I feel ought to come back because it's got a way to do that and generate models. And so, you know, so unless I can get the deep networks to do that, which seems unlikely, they can be eventually used as components for this type of thing, but not much more. One more slide, I think. Yeah, okay. So I think we need to develop ways of, you know, instead of the standard idea, you train on half the data set, you test on the other half, and then you have a small bit for validation. You have to move to a pattern where you're learning from a limited size data set, because the whole thing is going to be exponentially big. And then how do you test on the infinite data? So here, you can't test over all of them for the same reason you can't train over all of them. So there I thought the idea was you should really generalize the idea of attacks. You know, let your worst enemy, I was at UCLA, so I'm not sure. You might know what I mean by that, but anyway, let competitors to try and see how they could break your algorithm by not just putting in this tiny little amounts of noise in this current atmosphere, but more structured things like throwing inclusions in front of the things, changing the properties, changing the viewpoints. How you search through that type of thing systematically is a bit unclear, but I think that's sort of the type of thing that you can do. Otherwise, I can't see how you can search through that enormous type of space. A guidance for cognitive and neuroscience, I haven't said much about that because the things I've got that may be interesting, I'm not sure, they're not quite ready to describe yet. But I certainly believe the human visual system is much more flexible and general purpose than any computer vision system. We can generalize to many things we haven't seen, we can extrapolate better, we can perform many different tasks at the same time. You know, we have causal understanding and our brains only use 1 watt of power compared to, you know, a 4 GPU machine is 1,500. Causes the fuses to crash in our CS building, and you know the brain can do it with 1 watt of power and 20 watts to keep the brain alive. You know, there's something we're missing there. And I think for cognitive science, it provides challenges for computer vision. If humans can do it, then ultimately machines should be able to do it. That's if we want general purpose vision or general purpose intelligence. And you know, so I think having the two fields together is very good. If I talk to the people, you know, there's a whole lot of overexcitement about deep networks, particularly by people who don't know anything about biology. If you talk to the biologists, they're far more level-headed and sane about this, but, you know, otherwise, particularly from California, you have a whole lot of over-enthusiasm and equating of neurons and neural networks with real neurons in the brain, which are arguably more complex and more variable. So I tend to think so I would argue that the two areas, cognitive science, neuroscience, biological vision and human vision would work together, and so it's very nice to see that happening here. So, conclusion, I think that, the deep nets are very useful tools for many applications, but they should probably be thought of more as one of the many tools that computer vision researchers have started picking up, starting with PCA, SVD, Markov models and things like that, than being the sort of the final solution you want to have. They can be used as components. They're very useful for that. They are evolving and adapting with many things they can do now they couldn't do a few years ago, but ultimately I don't think they're capable of doing it. Risks that AI would take over humans as science fiction, well, I'm not sure anyone believes that in this audience, but soon I think the exponential complexity of the data is one of the big problems we haven't dealt with. I don't know if people ever were aware of the Lighthill report of AI in England in the 1970s. It was a criticism of AI that reduced funding in England for AI in the long term, and Professor Lighthill was a mathematician. The one point that he made that I really agreed with was how to deal with exponential complexity. And I would say in vision we still don't know how to deal with it, and until we know how to deal with it, we won't really have AI. I would disagree with Lighthill because I think examples that he gave of what he thought were exponential complexity, I'm not sure they are. They're big, and the medical images may be one example. They're big, but they're not exponential. If they're big, the deep networks might be able to deal with them, or other methods of that sort. But then beyond that was the exponential thing, and I can't see the deep networks working on it. And so I think, again, I think it takes time to develop systems like this, and it requires, I think, the study of all the things together, which of course is what's being done here in vision. Okay, so sorry I went on a bit over, but that's the talk, that's the end.
So I think we've got time for a couple of questions. Okay, well, I'm going to ask the first one then. So the visual system is subject to illusions. You get lots and lots of illusions, like if you're traveling for a little while and then you stop, you can go backwards, things like that. If your nets had, would it be a success if they had the illusion or if they didn't have illusions? Which would be the success?
I think I've hedged my bets. It depends on the illusions. I mean, things like not being able to see the gorilla in the room. A deep network could see. A computer vision, artificial intelligence system could see that, and there's no reason why. You can't imagine why it would not want to do that. I mean, that relates to some of the issues of medical imaging. Radiology experts are very good, but they have attention biases. It's sort of studied, it's known. They're not looking at over the whole thing, they may be missing something. So I think there are certain aspects of human vision, maybe like attention, which is tied into our biology, our evolution, or possibly even that's why we only need 1 watt of power. It's a quick method that works a lot of the time, doesn't hurt us elsewhere. And I would see for computer vision no need to do that. Similar things like having phobias and non-phobias, I'm not sure whether you need it.
So your aim is not to model the visual system, but to achieve vision.
It's to achieve vision, but I would say other ones seem to be due to what I think, Marr would call natural constraints and Gibson would call ecological constraints, with the idea that images, certainly, for a single image, they're really unconstrained. There are many possible interpretations you need from your model about the world in order to interpret them. And those assumptions, they can be useful, most of the time, and every so often you can find cases where they're not, and that's an illusion. So I think those I wouldn't mind about. Some of the students studying adversarial networks, I say, what are adversaries for humans? And when I look into it, the adversaries are usually what's called, accidental alignments. You have somebody, a woman, standing on a beach towel with a shadow that appears to be thrown by her towel, so it appears that she's levitating, but in fact the shadow is thrown by something else.
Yeah.
So the human illusions of that sort, if it's rich enough, there are not that many of them, and they seem to be actually pretty sensible techniques, and maybe that's an illusion for one image or something. Of course, the situations where you're doing and you're putting people in environments when you're messing up gravity and everything else, that's another aspect altogether. And I wouldn't think humans can survive that, and if if you want to send robots up, well, robots can survive that. If you want to send robots up into space, it's probably a good thing that they can. But it does seem like there's a core problem which is common to humans and machines, which is you've got light rays, you're constructing the 3D world, how on earth do you do that? That's a core problem.
Right.
And I think you need assumptions about world to do that, and certain illusions, could well be in common. Yeah.
Couple of questions, very nice talk. If you have a net with, what was the maximum, 1,001 layers or something like that?
Yeah, I'm not sure that's the maximum now.
Well, but that's totally non-biological.
Oh, absolutely.
And given your approach where you reduce the number of layers by increasing the number of nonlinearities, surely feedback does that, right? If you have nonlinearities in 2 layers that are feeding back to each other, each time there's a cycle, there are in principle twice as many or whatever nonlinearities.
Yeah.
And has anyone tried to exploit anything like that? Because that is present in the visual system.
Yeah, no, I mean, certainly an issue about the deep nets is the entirely bottom-up type thing, and obviously for bottom-up, top-down is there. I don't know any nice models of that sort. I know people try them, but they all seem rather unprincipled, I think. I mean, I think your models are not really deep network models. You've got sort of principles for how the top-down goes down. But the deep networks I've seen is, okay, we've got feedback up there, now let's put a layer that goes down, and, why should that do anything useful? I think the issue about having that many layers, I mean, it's sort of like, these are ResNets, so ResNet layers can just be doing the identity mapping. It's sort of, instead of modeling the weights, you model 1 minus the epsilon and stuff like that. So the advantage of that is you can train them, you don't really overtrain them too much, and they do slightly better. But I think in terms of efficiency, you don't need anything that big to do it. And you can do it with the smaller things like we've described, or having more filters. Okay, so B1 and B2, that's full of immense number of possible filters you can have. And then, as you say, when you bring in things like top-down and stuff like that, yeah.
Okay, so I just have one more question first.
What would you say are the main obstacles right now in deep neural networks learning more causal rules?
Well, I guess first thing is most people don't think in terms of that. I think, I would say the deep networks need to get some sort of factorization in. If you take an image, an image generated by computer graphics, image is a product of the geometry with the lighting and the albedo, that's a factorized thing. If you want to, deal with this geometry, the shape, and then there's the appearance as well, that's again factorizable. Those things are not in the deep networks. Jeff Hinton has some, attempts recently in low-level ways to put in some of that factorization, and it's something that's an idea that's come up every so often, but it's not in there directly at the moment. So that's one aspect. I'd say I think they also want to be more interpretable. You'd like them to start becoming symbolic, which is almost like they would want to extract out the fact that this isn't just always a gabor, but that could correspond to an edge, and then the edge could be grouped with other edges in some way. So abstraction, symbolic, is sort of, it's a way of getting something that's not just the particular set of patterns you've looked at in the data set. And I think you're going to need that, because otherwise, unless you can train on every possible pattern that's ever happened, unless a representative set of them, you're going to have difficulty. I think. So I think the hierarchies are very good. I like them. I just think they need to be a lot smarter and have those sorts of components within them.
You really want to?
That's okay.
You can talk. Well, you talk first, yes. Okay, so thank you very much. Now, when Ian Howard died, his wife made a large donation to the university, and the interest from that has been used to support an incoming graduate student. And so we have a nice little certificate here to give to the winner for this year, Lena Musa. If you're here, yes? Do you want to come down and have a photograph? Tony Howard will be able to be here to present it herself, but she doesn't seem to have made it, so
Away from the TV.
Great, thank you, congratulations.